Okay, today's topic is the analytic properties of conic sections. Now, all of this material was in the reading, and I realized that was a lot of reading. A couple of you contacted me and said, "What are we supposed to do?" I said, "You read and study." That was it's a big section. It's the biggest section in the book. There's a lot of information there. Now, I've posted this document on the shared drive, and actually, it's a lot better if you look at it on the drive because it's in color. And that really does help, the color. But I have it here because I'm going to draw on it a little bit to show you a couple things about it. So I would look at it on the shared drive and just look at it on your computer screen. You don't necessarily need to print these out. I always did for the tests, but I'm not going to do it that way anyhow, so I wouldn't worry about that too much. All right, these are the properties of ellipses, and these are the properties of parabolas. Now, the ellipses have a lot in common with the hyperbolas, and we'll get to that diagram in a second. These equations, C is equal to EA, A is equal to ED, A squared is equal to CD, D2 is equal to ED1, those are all common between ellipses and hyperbolas. We'll just write E and H. Now, this is unique to the ellipse. It's the two-focus property of the ellipse. There's some interesting videos online if you want to look at it as to how this works. I have some good Geometry Sketchpad stuff, but we're not going to see that, obviously. And I'm not going to talk about that too much here. This is important in that a squared is equal to b squared plus c squared. Now, it's called the Pythagorean property of the ellipse, but it's not the way you would normally think of the Pythagorean property. You know, the Pythagorean theorem isn't a squared plus b squared is equal to c squared. It's leg squared plus leg squared is equal to hypotenuse squared. And that turns out to be true in here on the two-focus property of the ellipses. All right, now if I pick this point right down here and draw D2 and D3, they form two congruent right triangles. And since D2 plus D3 is equal to 2A, if these two are congruent, that means that D2 and D3 both have to be A. And that makes this segment right here equal to A if the point is right there. And that's why we have A squared is equal to B squared plus C squared in the ellipse. Now, if you didn't understand what I talked about right there, you may want to print this thing out and go back and look at it. A couple other things about this. Here's the directrix. And it's hard to see in this diagram, but it's not as hard to see in the color diagram. But this distance from the center of the ellipse to the directrix is known as D with no subscript. It's called the directrix distance D. It's the distance from the center of the ellipse to the directrix. Now, D1 is what we talked about in the other videos. Distance from directrix to conic. D2 is from focus to conic. D3 is also focus to conic. It doesn't show it on this diagram, but the ellipse also follows the focus directrix property on the other side over here. I mean, I could draw the D2 is equal to ED1 from either side, use the special graph paper from either directrix, and it would draw this ellipse the same way from both sides. And that's an interesting property of the ellipse and the hyperbola for that matter. And the parabola doesn't have that property. Interestingly enough, the parabola has only one directrix. So, you know, I guess I could talk about this for a long time, and normally when we have a 47-minute class, I do. And it takes a couple days to get over this stuff, and we are going to spend a couple days on this. So, you know, go back and review all these properties for the ellipse and the parabola and the hyperbola. Okay, but let me move on to the parabola. Now, this is a much simpler situation. The parabola has only one focus and one directrix. It doesn't have two of each like the other two. And the only thing you really have to know about the parabola is this, what distance is called P. Now, the P is the distance from directrix to conic and focus to conic at the vertex. Seeing how this is the shortest distance between the directrix and the focus, this P is equidistant from either of these things to the conic. And it's related to A, like in ax squared plus bx plus c, this A. 1 over 4p is equal to A. That's really the only thing you need to know about the analytics of the parabola, is that this distance P defines the shape of the parabola. Now, of course, d2 is equal to ed1 applies to the parabola with, in this case, the eccentricity being 1, d2 is equal to d1. Okay, let me slide the hyperbola in here. Okay, again, the hyperbola properties, and this is on the drive for you to see. These 4 properties, of course, apply to ellipse and hyperbola. I mentioned that on the ellipse side. The hyperbola has what's called the constant differences property, that the difference between d2 and d3, which are defined the same as on the ellipse. Focus to conic, those are d2 and d3. Directrix to conic, d1. Same thing for focus directrix property and for this property. Although with the hyperbola, it's the constant difference property, whereas with the ellipse, it's the constant sum property. Now, the Pythagorean property for the hyperbola is what you'd expect, I guess. A squared plus b squared is equal to c squared. One thing I didn't mention back on the ellipse was c is called the focal radius. It's the distance from the center to the focus. Now, let me go back to the ellipse because I didn't cover that sufficiently, let's say. Back to the ellipse for a second. A in the ellipse, distance from center to vertex, is called the semi-major radius, or the major radius, I guess. From one end of the ellipse to the other is the major axis. The major radius is from center to vertex, in the longer direction. The shorter, B, is called the minor radius, and this is the minor axis. Now in the ellipse, the longer is always the major, and the shorter is always the minor. In the hyperbola, A and B don't have names like major axis and minor axis, but the distance A is always the distance from the center to the vertex. The distance B doesn't really show up on the hyperbola. It's in this right triangle here, but I'm not going to spend much time on that. It's based on the Pythagorean relationship. That distance is A, center to vertex. C is the focal radius, here to here, and there is this relationship there, and it's very difficult to figure that out. I don't think there's really any way I can do it on a piece of paper. I try to do it with the geometry sketch pad during class, but we don't have that luxury. So just take it for what it's worth, that the relationship between these 3 quantities, A, B, and C, are right here. Now, when we write these in Cartesian coordinates, the slopes of the asymptotes is always the y dilation divided by the x dilation. An important point to remember about hyperbolas, as far as this stuff goes, is that this distance A is always from center to vertex. If the hyperbola happens to open side to side, that A is associated with the x-coordinate. If the hyperbola opens up and down, the A is associated with the y-coordinate. A does not have to be larger than B. A can be smaller than B. But A has to be from center to vertex. Okay, now your assignment tonight is based off of this sheet, which is posted. Let me see if I can get that into the right spot here. Okay. And you're given, this is from the old book, you're given different things about the conics. We're going to work off of this side today. Tomorrow we'll work over here, and I have some other examples for you there. Now your directions are, and they're up here, find A, B, C, D, and E for each ellipse and hyperbola. Find the P for parabolas. Sketch a graph, and this should be right, and equation. I got an extra D in there somehow or another. I should have noticed that years ago, I guess. In center and radius or general form, possibly both. Okay. So notice this is from the old book. They wrote it a little bit differently. Instead of center and radius form, they wrote x squared, say, over 169. We would write x over 13 quantity squared in center and radius form. And as I do the examples, I'll show you that. Okay, let's get to the examples then. Okay, let me see. Blank piece of paper. There we go. First is number 9. Now the book says that this is x minus 1 squared over 16 plus y plus 2 squared over 9 is equal to 1. In center and radius form, we write x minus 1 over 4 squared plus y plus 2 over 3 squared is equal to 1. All right, well, we can glance at this and find some different things. Remember, with an ellipse, as I said before, A and B are these numbers. The larger of them in an ellipse is A and the smaller is B. So we can just write that down. A is 4, B is equal to 3. Now, if I'm going to find the focal radius, you might be fooled into thinking that it's going to be 5 because A squared plus B squared is equal to C squared, but it doesn't work that way. For the ellipse, remember, A squared is equal to B squared plus C squared. So that makes C equal to the square root of A squared minus B squared. So in this case, C must be equal to the square root of 7. All right, well, from the other equations that I gave you, and maybe you should have this document open on your desktop or whatever on your screen. I mean, I got so many things open at this point. But I can find the directrix distance, which is A squared over C, and that's right off of the equations. I just isolate that for D, and I get A squared over C. So that'll be 16 divided by the square root of 7, and the eccentricity is C over A. Now there's an equation on the sheet that says C is equal to EA, isolating for E is equal to C over A. So in for this particular ellipse, that is the square root of 7 over 4. That's the eccentricity. All right, now I will post on Desmos, and you guys go to Desmos, and I'll post. I got graphs on Desmos, and I'll give you the link for this. And this is the ellipse we're looking at right there. Okay. Center at 1, negative 2. Major axis of 4, major radius of 4, minor radius of 3. So if I go from here to here, that's 4 units. Here to here, that's 3 units. From here to here, that's the square root of 6. Now I have on my equations over here, x is equal to 1 plus. Now remember, this is the directrix distance D is from center to focus. 16 divided by the square root of 7 is directrix distance D. If I add that to the coordinate 1, which is the center, that gives me this focus, and there's the other focus. Or, pardon me, this directrix and this directrix. Okay. Now, the focal radius square root of 7, this, let me go back. This is the directrix distance from here to here and from there to there. You can see them plotted with the dotted lines. And that's how I started with this, the dotted lines for the directrices. Okay, the focal radius is the square root of 7. These 2 points are plotted as the 2 foci. Some people say foci, some people say foci. It doesn't really make any difference. All right, so here, this is this ellipse graphed for you. One thing I'd like to point out is that at the vertices, say right here, notice how that vertex is closer to the focus than it is the directrix. And that should make sense because this distance is d1, that's d2. Remember, d2 is equal to ed1. For the ellipse, the eccentricity has to be less than 1, so d2 should be less than d1. Think about that for a little while, and if you have to rerun that portion of the video, go ahead and do it, because you should understand that concept. All right, well, we can also come up with we have this in center and radius form right now. We can get general form by noting the LCD is 4 squared times 3 squared. Multiply through by the LCD. 4 squareds reduce. I get 9 times x squared minus 2x plus 1. The 3 squareds reduce. I get 4 squared, or 16, times y squared plus 4y plus 4. And that's equal to 1 times the LCD, or 144. Okay, exercise left to the student. And you can do this. You end up with 9x squared plus 16y squared minus 18x plus 64y minus 71 is equal to 0. Well, note my graph, and I'll give you this link. These two are right on top of one another. They're the same thing. They're just written, one in center and radius form, the other in general form. Okay, so when you do your homework tonight, this is what I want you to do. Or I guess there's really not homework. The assignment, I'm going to call it. Find these values, A, B, C, D, and E. Write these equations for the homework problems. And make a Desmos graph. Okay. All right, let's move to number 11. Now out of the book, or out of the extra sheet, I should say. Number 11 was written like this on the sheet. X minus 3 squared over 16 minus y plus 2 squared over 16 I take that back. All right, you can do number 11 for homework. I did number 12 as my example, so we'll do it like that. Number 12 was the opposite of x plus 1 squared over 9 plus y minus 2 squared over 16 is equal to 1. So I'll do number 12 as an example. You can do number 11 for homework. I screwed that up, but I'm not going back and changing it now. That I can tell you. All right, if we're looking at this, and let's make sure I got that right. Okay, we're good. Okay, now looking at the, changing this to center and radius form, this will be x plus 1 over 3 squared, y minus 2 over 4 squared is equal to 1. Okay, the value of a here, you go to the positive term. Be it the largest or the smallest, it's the positive. A is 4. That makes b equal to 3. And in this case, since c squared is equal to a squared plus b squared for the hyperbola, c is equal to 5. Same equation for ellipse and hyperbola. D is equal to a squared over c, which is 16/5. And e is now 5/4 because the c is bigger than the a. And that makes sense because a hyperbola has a eccentricity greater than 1. All right, we're going to take a little different approach. And sometimes this isn't bad to find the general form. Okay, so what I'm going to do is I'm going to look at it from this perspective right here, and that's -1/9 times x squared plus 2x plus 1. This will be 1/16 times y squared minus 4y plus 4, and that's equal to 1. Distributing, negative 1/9 x squared, negative 2/9 x minus 1/9. I shouldn't have that there. Plus, distributing 1/16 y squared minus 4/16, which reduces to 1/4 y, plus 1/4 is equal to 1. In general form here, we have negative 1/9 x squared plus 1/16 y squared minus 2/9 x minus 1/4 y, and then we have this, and I'll even write these as all, just adding them together because that's the way I put it into Desmos. We have negative 1/9 plus 1/4 minus 1, moving that over is equal to 0. Okay, let me get my Desmos. And Desmos is awesome. Okay, so this is, it says number 11, but I'll change the name on that to make it okay. All right, there we have it, and over here we have that stuff in there. You can look at that later. But here's these two things, of course, are the same thing. Here are the directrices. Now, another thing to note about the directrices in the hyperbola is they are between the two branches. Now, they have to be. That makes total sense knowing what we talk about, because a directrix can never intersect the conic itself, because there has to be some sort of distance between them. So the directrices have to be in between. Now that means that the directrix distance between center and directrix has to be smaller than the focal radius, and it is. And you can verify that when you look at this, and again, maybe you can go back and look at the video again, and you can look at all the equations I have on the the Desmos that I will post the links to. All right, here are the two equations for the conic. These are the directrices. That's the y value of the center plus the directrix distance, y value of the center minus the directrix distance. That's the center, and these are the two foci. Okay, you should look at the the notes. You can stop this. Hopefully you'll be able to see it, and you can look at these on your Desmos at home. Okay, we got one more example, and that's a parabola. The parabola is much easier, actually, and that'll be number 17 is the example. So you'll do number 18. All right. Y is equal to 1/12 x squared minus 2 is how it comes in the book, and that's, you're very familiar with that. Now, recall from the sheet that I posted for you that this value, a, in the y is equal to ax squared plus bx plus c is equal to 1 over 4p. So 1/12 is 1 over 4p. That must make p equal to 3 just by inspection. Now, what is that p? That is the distance from the focus to the vertex, or from the directrix to the vertex. Okay, so here I will go to problem number 17, and again, let's see if I can put this so I can see everything at the same time. Hopefully we can. I'm hoping that this is all good. Let me see, move that back down just a bit. Okay. Oops. All right. Okay, the problem, like I said, is fairly simple. All right. This distance from, there's the vertex, and that's from the equation 0, -2. So the vertex is at 0, -2. If the distance p, which is the distance from directrix to vertex or focus to vertex, is 3, that makes the directrix, the horizontal line, y is equal to -5, and the focus at 0, 1. Now, just as a quick check on this, that if you look here where the x-intercepts are, if 0 is equal to 1/12 x squared minus 2, that must make 2 equal to 1/12 x squared, or x squared equal to 24. X must be the square root of 24. So that puts the x-intercepts at negative square root of 24, comma 0, and square root of 24, comma 0. The distance between either of these points in there is 5. 5 from here to here, and it's also 5 from the x-intercept down to there, because the shortest distance between a point and a line is the perpendicular distance. That satisfies the definition of the parabola, which has to be d2 is equal to d1. Well, d2 is always equal to ed1, but d2 is equal to d1 for the parabola itself. Okay, now that is a long video, I'd say. Your assignment is on the extra sheet, which is posted. You'll do numbers 10, 11, since I did the wrong one, and 18. Okay? So you do not have to do these on the special graph paper. What I'd like you to do is work this type of stuff out. Here, let me slide this back down. Let's see, work these things out like I did, and then graph them in Desmos, or look at my graph in Desmos. I guess you don't have, you should graph the ones that you do in Desmos, especially like this. Put this in there and put that in there. Make sure it's right, and make sure it's consistent with what you're getting for these numbers for all of these different values. Okay, we'll see if I can get this thing posted. It's a longer video today. We'll see you next time.